Okay, so these are all of these different gas laws. And the funny thing is that all of these scientists basically found this around the same time when they were sitting there doing their experiments. So you have Charles' law, you have Gay-Lussac's law, you have Boyle's law, you have Avogadro's law. Charles' law is comparing volume to temperature. Gay-Lussac was comparing pressure to temperature. Boyle's was doing volume to pressure. And so if you actually start thinking about it, all of these are the four characteristics that you use to sit there and kind of provide properties of gases, right? So what happened was someone came along and said, you know what? I bet you we could sit there and combine all of these four properties: volume, temperature, number of moles, and pressure. And so that's exactly what they did. And they tested out, of course. Now, this represents what we call the ideal gas law. It's ideal because we're making a couple of assumptions. One of the assumptions that we're making, I have no idea what's going on with my screen here. Yeah, there we go. One of the assumptions that we're making is that the gases are behaving, quote, ideally. You guys know what I mean by ideally?
No.
Like the ideal gas?
Well, let me tell you what I mean by ideally. So in reality, you have intramolecular forces, forces that act on molecules, between two molecules, two independent molecules. So, you know, it's kind of like water, right? Or steam in this case. So steam is polar or nonpolar. You guys remember? Or water. It's polar or nonpolar. Polar. H2O. Oh, I forget, wrong class. If you're in 2A, you should know this. Well, let me tell you, it's polar, right? And the reason why it's polar is because, look at this. Hydrogen and oxygen are sharing a bond. So this bond is being shared between them. We've kind of talked about this covalent compounds and how to name covalent compounds and all that stuff. Covalent compounds are basically things that are going to be sharing electrons. Water shares an electron. However, oxygen wants those electrons much more than hydrogen. And since oxygen wants those electrons much more than hydrogen, oxygen is going to be like the selfish brother and say, hey, the electrons are going to come on my side most of the time, right? So I'm going to keep the electrons, okay? Where hydrogen will get it, but not get it that often. So I like to compare it to like me and my sisters. So me and my sisters, we were a poor family, right? And growing up, my parents would actually decide to buy us one like really good gift. And then we'd always get underwear, socks, and stuff like that, stuff that you needed. That was your Christmas gift. That was your main Christmas gift. And we would get one gift that we'd have to share. And one year we got, it was an Atari. You guys, your equivalent of the PlayStation, right? And not quite the same, but, you know, let's pretend, okay? So we got a brand new Atari. And, you know, we had, what is that? Pong, where the ball just goes bounce up and down, and you had Frogger, and you had, you know, there was like 3 or 4 games at that time. So I was like an Atari king, right? Because I'm the oldest of all my siblings. So the rule was, once we got our gift, I would play with it most of the time. And then as soon as my mom got home from work, my mom worked 2 jobs. So she worked most of the day. But when she was getting home, I would actually stop an hour early so I could cook and kind of straighten up everything before she got to home from work, because otherwise I was going to get in a lot of trouble. And then, and so I let my sister start playing with it then. So I would play all day long. And then an hour before my mom comes in to work, I stop playing and give it to my sisters. And then as soon as my mom comes home and everything like that, I'm like, okay, it's my turn, you know, and so I act like, you know, they've been playing with it most of the day, right? So is that fair?
No.
No, what do you mean it isn't fair? It's
To
perfect.
you, it was.
Yeah, it worked great for me. I thought it was ideal. It's perfect, right? So I got the Atari, about 80 to 90% of the time, and my sisters got it for about 20 to 10% of the time. Fair, right? Are we sharing? Amanda, are we sharing?
Yes, we are.
Yeah, we're sharing, right? It's great being the oldest, right? We get to set the terms of sharing, right?
Sharing, but in
So,
a small, like in a small time, like a little bit of time for them.
yeah, but they get it, right? Nonetheless,
Yeah.
it's sharing, right? So that's the same thing that happens here between these electrons. Electrons are being shared, right? But oxygen is getting it the majority of the time. And since we know that electrons have a negative charge, we define it as partially negative. And hydrogen has a positive charge. We define that as partially positive. One's partially negative, one's partially positive, right? And because they're partially, they're not complete. They're not like ionic compounds. They're not that complete positive and that complete negative. They're just partially, because the electron is spending more time here, but is able to go back to the other side a little bit. Okay, you guys kind of see that? Can you visualize that? Just think about me and my sisters. They'll tell you great stories. Okay, questions, concerns, cash, credit, cookies? Great, okay. So because they form this partially positive and negative charge, they also interact with each other. You'll have a hydrogen from the other molecule interacting with that oxygen because it's partially negative. This forms this it's a weak interaction. It's not a really strong interaction, but it's called a hydrogen bond. The reason why it's called a hydrogen bond is because hydrogen is interacting with it, right? And it's not really a bond. It's kind of a loose term. It's an interaction, truly an interaction. But somebody got real happy in biology and they said, oh, we're going to call this a hydrogen bond, where it's not truly a bond. Okay, questions, concerns? You guys kind of get that so far? And so I like to depict my interactions as just lines, So this is a weak interaction between these guys. They're not really bonded to each other, but they're interacting with each other. Now this happens, and this continues to happen with all of the water molecules in there, right? Because of that interaction, because of that partial negative and partial positive, they interact between molecules. This is one molecule, this is another molecule. They're able to interact. Can you guys see that? Matthew?
Yeah, I see that.
Good. Okay, so because they're able to sit there and interact, we have to take that in consideration if we're actually taking it under non-ideal circumstances. Ideal circumstances basically means that we're pretending that they don't physically interact with each other. They just kind of bounce off each other. So if you had, this is going to represent a molecule right there. If I had one molecule, it'll come, bounce off the other one, and act as if it's not going to stick at all. But that's not reality. Reality is that they stick, kind of like us. We make connections with people, sometimes negative connections, sometimes positive connections. Because of those connections, we kind of either, oh, that's my buddy, that's my road dog, I'm going to hang out with them, right? Even though that, you may want to be individuals, but sometimes you make that connection. That's the same thing with molecules. They're going to sometime make connections. And that's going to affect how they behave, right? So it may take you 5 hours to complete a homework assignment. If you guys are working in too big of a group and you got, someone like me that likes to tell stories and stories and stories and stories, then you'll end up being there for 5 hours where it would normally take you about 2. With the right group, that is just like, okay, let's get this done, You guys kind of see that?
Yes.
And so sometimes too much, too many people, too many molecules together can be a drag, and that's going to affect those properties. Those are non-ideal properties. So what we're assuming is that under the perfect circumstances, these guys are just going to bounce off each other. They're not sticking. So you don't have any molecular forces to worry about. That's one thing that we're talking about. The other thing is that we're assuming that we're under low pressure, because if you're under a lot of pressure, you're going to force things to start interacting with each other, whether you like it or not, because you're putting so much pressure on the system. So we're under a certain pressure range. So it's a pretty overall, in the big scheme of things, it's a low pressure, right? Typically, we're talking about 1 atmosphere or something like that, up to like 10, maybe 15 atmospheres. Once you get above that, that's considered high pressure. And that's going to change the behavior. And they're not going to behave ideally. The other thing is that we're assuming that we have relatively high temperature. We're not working at really low temperature. Because if it's working really low temperatures, the molecules are moving really slow. So if they're moving really slow, there's a stronger possibility that you'll have interaction. Okay? Do you guys kind of get that? Okay, so 3 things. One thing is that we're ignoring the intermolecular forces. 2, we're assuming that it's under relatively low pressure and high temperature. That's the 3rd one. Okay, so those are the assumptions that we make with the ideal gas law. Are you with me? Good.
Yes.
Yes.
Okay, so PV equals nRT, right? You merge all these together, that's what you're going to get, where R represents the combination of all of these Ks that come together. All those Ks are constant. So now we have this one new constant that we call R. We call that the ideal gas constant. Or you'll also see it as the universal gas constant. The universal gas constant, or the ideal gas constant, is 0.08206. And that's liters, atmospheres, moles, Kelvin. Now the units are going to be very important because if we change those units, we're going to change that value. Even though it's a constant, it's still going to be the same thing. But if I decide to use torrs, I have to sit there and adjust this so that I'm converting the units to torrs. So how many atmospheres are in a torr? One atmosphere equals how many torrs, I should say?
760.
Yeah.
So 760 torrs equals one atmosphere. So atmospheres are going to cancel out, and then I'd have to multiply this guy by 760 torrs. Nothing is working today. Okay, you guys see that?
Yeah.
Matt,
Yes.
you see it? Good. Okay, so all it is a conversion, right? So if you get something that doesn't fit that area, you can convert it, or you can convert it all to atmospheres. So you make sure that all of your units are in the right units: liters, atmospheres, moles, Kelvin. So if you have them in the right units in the beginning, when you plug and chug, you have nothing to worry about. Okay? Simple?
Yes.
Good.
Yes.
Okay. So let me ask you this. So an ideal gas law basically accurately describes the properties of ideal gas. So what is an ideal gas? And what are the assumptions being made about an ideal gas?
That it's at STP.
It's at standard temperature and pressure. What is STP?
Yeah.
You sure that is at
Uh,
STP? Or are you just
1
pulling shit up?
No, 1 ATM, 0 Celsius, and
So if
then
it's 0 Celsius, is that cold?
yeah.
Okay. So are we making the assumption that it's at STP then?
Okay, no. And the one I'm trying to remember the temperature. I don't remember the temperature of it.
Yeah, so we're not making an assumption for an ideal gas. We're not making an assumption that it's at STP. STP is a special circumstances which happens to kinda, not completely, falls into that range. What were the things that I just said? This is my testing you guys. Do you guys listen to anything that I say, or am I just talking?
Low pressure and high temperatures.
Low pressure and high temperature. Those are the two assumptions. What is the third one?
That it
We're
doesn't.
ignoring the intermolecular forces.
That's right. We're ignoring the intermolecular forces. Good job. Okay, so those are the assumptions that we're making, right? And so that's going to be crucial for us to use this equation. Otherwise, if I tell you specifically, this is not low temperature, low pressure, high temperature, right? If I clearly say that, then you're going to say, oh, we got to use the non-ideal gas law. Okay, questions, concerns, Cash? Okay, perfect. Okay, so we do have STP. This brings us to STP. And STP does kind of fall into the range. Only thing, 0 degrees Celsius is kind of pushing that limit, right? It's kind of a low temp. It's lower on the lower end. It's not, quote, a high temp, but it still kind of falls within that range. We're not getting, we're not getting 0 degrees Kelvin. So we can still kind of use it under these circumstances. Okay, so STP, standard temperature pressure, 0 degrees Celsius or 273 degrees Kelvin and 1 ATM. So Christian, you're right, but we're not just saying that pertains at ideal conditions only, okay?
Mhm.
Okay, so at STP, if we have 1 liter of gas, can you calculate the volume? Okay, ideal gas law, can you do it?
Yeah.
What do you get?
Well, isn't it standard 22.4 liters?
That's right. It's 22.4 liters at STP, right? And that's for 1 mole of any gas that's behaving ideally. So it could be carbon dioxide, it could be oxygen, it could be anything, right? As long as we have 1 mole of it, and we're at STP, you're always going to have 22.4 liters. Okay, so that's also kind of the beauty of using STP, standard temperature and pressure. The pressure and the temperature are always going to be 0 degrees Kelvin or 273 Kelvin, 0 degrees Celsius, 1 atmosphere. Okay. Questions, concerns, Cash? Good. Okay, so we can also use this equation to calculate density. What is the units for density?
Grams per milliliter.
Grams per milliliter.
Mass over volume.
So generally, it's just mass over volume, right?
Mhm.
Can we get mass over volume from this equation?
If you rearrange it, yeah.
Yeah, if we rearrange it, we can sit there and get mass over volume because we know that the number of moles in is going to be the mass over molar mass. We know that density, rho, is equal mass over volume. So if I plug this back into my equation, I get PV, M over capital M, RT, and I solve for MV, which is rho. Okay, piece of cake. So if I know the molar mass of the gas that I'm working with, which I should know if I know the chemical compound, all I need is to know the pressure, the temperature, and I know the ideal gas constant is always going to be the same. What is the ideal gas constant again?
Zero 0.0826.
8206. Yes. Good job. Okay, so this is just basically showing you actually what I just did on the screen, right? So you have a copy of it so you'll remember. Okay, questions, concerns, Cash? So let's go back to our equation here, not this one. So is there a way that I can calculate molar volume, right? We know molar mass, but can we calculate molar volume? What is the definition? What is the definition of molar mass? What are the units for molar mass?
Grams per mole.
Grams per mole. So what do you guys think are the units for molar volume?
Moles per liter.
Is it moles per liter or is it liters per mole?
Liters per mole.
Yeah. So oops. So molar volume is just going to be RT divided by P. If we calculated STP, at STP, standard temperature and pressure, right? What was the value that you got? Christian?
The 22 point, that one?
Yeah.
22.4 liters.
So at STP, our molar volume it's going to be 24.4 liters per mole, which is great for us, right? Because we know that's always going to be the case at STP. So if they give you a question that has STP and they say, calculate the volume, all you need to do is multiply it by the moles, the number of moles that you're looking at, right? And then you already have your answer, 22.4 multiplied by the number of moles. Simple?
Yes.
Good.
So it's literally just algebra based on which one you're wanting.
Exactly. And that's the beauty of the ideal gas law. It's just algebra and then it's plug and chug, right?
Okay.
You write down what you have, you write down what you need, it's plug and chug, really.
And you always want it in moles if you're given grams.
Yes.
Okay.
Yeah. Although you can use grams, right? Because all grams is divided by the molar mass, right? So you can use that. Correct? And so in ways, we can sit there, if we're given the pressure, the temperature, the volume, and the mass, we can calculate the molar mass. And that's what this is basically showing you. Okay? So by playing with the equation algebraically, we're able to solve so many different things. Okay? Are you with me?
Yeah.
Yes.
Okay, good.
Yeah.
I'm glad you're here. Okay, so now we're assuming, we're going to make some assumptions here. If we have 3 different gases, like say gases that are make up air, we're going to make our own batch of air in a bottle, right? So we have oxygen, we have nitrogen, and we have hydrogen. Those are the three major components of air, and carbon dioxide. We'll say 4, right? So if we have nitrogen, hydrogen, carbon dioxide, and hydrogen, and we put them all in a bottle, are these guys going to interact? With each other?
No.
No, they're going to act independently, right? And since they're going to act independently, the pressure that's going to be introduced for the hydrogen, we'll say that's my PA. Plus the pressure that's going to be introduced from the oxygen, that's my PB, plus the pressure that's introduced by that carbon dioxide, it's my PC, plus the pressure that's introduced by the nitrogen. That would be my PD. Now, we just put these in a bottle, right? If we put this in the bottle, the pressure is just going to add up to the partial pressures of each of the individual gases, added all together. So the total pressure will be just the sum of all of the partial pressures. Simple?
Yeah.
And that's making an assumption. That's assuming you have an ideal gas mixture, and these guys are not reacting with each other. 2 assumptions, right? Ideal gas, and they're not reacting. Okay? So this is basically just showing you an example of that, right? So if I add up all of the different pressures for all of the different gases, they're going to add up to a total pressure. Okay, so this allows us, do you guys remember when we did parts? See, part over the whole. Do you guys remember that?
Yeah.
When we were talking about mass. Well, we can also apply this for moles as well, or pressure, right? So mole fraction, since pressure is directly proportional to moles, our mole fraction is going to be directly proportional to the pressure fraction, right? So P total represents the total pressure. PA represents only the part of mixture A, right? And so we could sit there and say our mole fraction for PA over PT is equal to X. That represents our mole fraction. Okay, and that's just saying part over the whole, right? And we can make that into a percentage if we want to by multiplying it by 100, if we want to do it for kicks and giggles, or we could just leave it as a mole fraction. Still with me?
Yes.
Good. Okay. So we have a reaction, right? And this is a really cool way of doing this. So our total pressure is going to be equal to the pressure of the water plus, in this case, we have a reaction that's producing hydrogen gas. And so we're collecting all of the hydrogen gas in our flask. So total pressure is going to be the pressure due to the water vapor, as well as the pressure associated with the gas that's being generated. So that's going to be our total pressure. Okay. Questions? So if this gas is collected in the, let's say collected in the flask, long as this doesn't completely push out everything, right? All the water. So then we know that the pressure of the gas is going to be equal to atmospheric pressure. Okay, So the total pressure is going to be equal to atmospheric pressure. So then if we know or we calculate the partial pressure of the water, the gas going through the water, that's going to be a partial pressure that's going to be associated with that water vapor. Okay? Questions, concerns? Cash? So this is going to be very similar to the manometer that we had talked about earlier. Okay? Okay, so water vapor. Water vapor is an intensive property, so it doesn't depend on the amount of water that's present. It is dependent on temperature. Okay, so the water vapor is going to be dependent on temperature. And this is just a curve that's basically showing that. So if you're given the curve, let's say we did the experiment at 20 degrees Celsius, right? Then we can sit there and calculate the water vapor based upon the curve, roughly. Okay, questions, concerns, Cash? Okay,
No, not so far.
not so far. Okay, so let's make it a little bit harder because, this is too easy. We're doing algebra and stuff like that, so let's do it where there's actual reactions. What happens if we have two things that are reacting? Right? How does that affect things? Right? So guess what? It's still going to obey the laws of chemistry. So we're still going to use stoichiometry. We're going to have a balanced equation. It's going to behave the same way, but now you have a way of calculating moles, right? PV equals nRT, right? If you're given pressure, temperature, and volume, you can calculate the number of moles. Or if you're giving grams, right? You can sit there and calculate the number of moles that way too. But it will still obey the rules of chemistry. So you're still going to use stoichiometry. Are you with me?
Mm-hmm.
Yep.
I wish my slides were with me. Okay, so because we can sit there and say that under constant temperature and constant pressure, the pressure and the temperature aren't changing, then we can sit there and make a couple of assumptions. Under constant temperature and constant pressure, we can say that due to Avogadro's law, V equals K over N. I mean Kn, where K is the constant, V is the volume, and N is the number of moles. Right? So under those circumstances, right, they're going to be directly proportional, right? Or in this case, it's going to be equal to the number of moles, right? So yeah, V equals Kn, okay? So then that allows us to sit there and say, if we have the number of moles, we can sit there and say, hey, we could easily calculate the volume, and we know that that's going to increase proportionally. Right? So here's the question. Come on. Let's assume we have 0.025 grams of lithium reacting with water. Calculate the pressure of H2 gas, assuming the reaction is done in a 25.0 milliliter vessel at 200 degrees Fahrenheit. What am I going to do?
Are you going to plug it into the idle gas equation?
We're going to plug it into the ideal gas, but the first thing that we need to do is calculate what?
How much hydrogen is produced?
How much hydrogen gas is produced. And so if we have 0.0250 grams of lithium, what do I need to do to calculate how much H2 we have? First off, is my equation balanced?
No.
No, it isn't. Okay, so what do I need to do to balance it? Aren't these the components? How many lithiums do I have on my reactant side?
One.
What about my product side?
1,
How many hydrogens do I have on my reactant side?
2,
And my product side?
3,
How many oxygens do I have on my reactant side?
1,
My product side.
1.
Okay. So I got 1, 1. So I need to work on my hydrogens. What can I do to fix my hydrogens? I have 3 on one side and 2 on the other. Any ideas? Let's see. Who's my favorite? Who's my favorite today? Christian,
Yes.
help me out here.
Let's see. So you would have to find the 2.5 grams. Wait, what if you balancing it, right?
That's correct.
Okay. 1 DM. You would have to have, 2 hydrogens on this side.
I'm not a mind reader. What is this side?
On the right side, my bad. On lithium, because on hydrogen, on the lithium hydroxide, since
Okay.
it's missing one, so you would have to add one. If you add one there,
Okay.
then it will give
So
you.
then that gives me 4
Mhm.
and 2.
Yes.
Okay. So what do I need to do now?
You would have to add 2 waters on the left. But then that would. Yeah.
Okay. 2 waters on the left. Anything else? So then
Well,
that
it
gives
would
me
be 4
4 and 2.
then 2 oxygens. And then you have to add another lithium on the, yeah. And then that's balanced.
Okay. So now we got a balanced equation, right? So once we have a balanced equation, what can we do?
Mole-to-mole ratio.
Mole to mole ratio. So do we have moles?
But you need your grams of lithium to 1 mole.
So grams of lithium. Lithium weighs how much?
7 grams.
You said 7 grams?
Yeah.
Something like that. And that's per 1 mole. Is that correct?
Yeah.
Am I putting in the right spot or am I messing up?
No.
Okay. Grams cancel out. We get moles.
So then you have 2 moles of lithium on the bottom to 1 mole of hydrogen on the top.
Okay. Moles of lithium. We're going to cancel out. And we have moles of hydrogen. Isn't that what we want? To work with our ideal gas law?
Yep.
Okay. So that gives me how many sig figs should I have?
3. 7, 1, 7, 9.
Okay. So I got N. And Amanda says that we're going to have to use PV equals nRT. And we're solving for P. Okay. So what is V?
The 25 milliliters.
So do I leave it in 25 milliliters?
Oh, you need liters.
Okay. So I have to convert this to liters. And I do that by what?
Just
Okay.
divided by 1,000. So
Divided by 1,000.
0.0025 liters.
Okay. What is R?
Constant.
It's a constant. What is that value?
0.0821.
0. Oh, you're rounding up. She getting fancy and all.
206.
Yeah. ATM liters.
Moles Kelvin.
I need an
Not being
intelligence.
fancy. I'm just going off of what I have here for you.
Okay, that's fine. Fine, you can round it up. It don't hurt my feelings. T.
93 Kelvin.
How much?
93 Kelvin.
93 Kelvin. How did you
Oh
calculate?
wait, no, that's Celsius. Hold on. So it's 366 Kelvin.
Okay, so how do I calculate that?
So you have to do 5 ninths times 200 minus 32, which is your Celsius, and then you add 273.15.
Okay, so you're saying I have to go 5 ninths times 200
Minus 32.
minus 32.
And you take that answer and you add 273.15 to get your Kelvin.
Okay,
That was 93.
okay. Make sure you said 5 ninths, right? And what did you say you got?
Well, because I put the 32 into the parentheses with the 200. I got 93, and then I
Okay.
added the 273.15, and I got 366.
Okay.
So then it should be 93 degrees Celsius plus 273. Yeah, I don't know.
Sounds good. Oops. Okay, so we get 366 Kelvin. So that's my temperature. So do I have everything to solve for P?
Yes.
Okay. So we have, what is that? 0.00179. Moles. Times our R, which is 0.0821 ATM per liter mole Kelvin times 366 Kelvin divided by 0. 0.025 liters. Okay, if we pay attention to our units, moles are going to cancel, liters are going to cancel, and Kelvin's going to cancel. So, what do you guys get?
0.15.
You get 1.15?
2.15.
Okay. And the units?
ATM.
Piece of cake?
Yeah.
Okay. Everybody got it down? Can I move on?
Mhm.
Yes.
Okay, good. Okay, so you guys have heard of the greenhouse effect?
Yes.
Yeah. Okay, so in the case of that, right? So we're heating up the Earth's atmosphere, and as a result of us heating up the Earth's atmosphere, we're getting so many gases that are produced in heavy abundance. How is that impacting the Earth?
Warming it.
It's warming it. So if we're warming it, what are we also doing? Is the volume of the Earth going to expand?
Yes.
Is it? You have gravitational pull, all that affecting it, keeping it kind of contained. Is it going to expand really?
Oh.
No.
So, but what are we doing in that case? If the volume isn't going to change, get this equation, PV equals nRT. So if I went PV 1 NT 1. Okay, so if I'm going from one temperature to a new temperature, we're heating it up, right? Earth's getting hot. you know, global warming and all that stuff, right? Our volume are going to be constant. What we have on the Earth is going to be pretty much constant, right? Number of moles are going to be constant. So we have V equals V2, and N equals N1 equals N2. So then we can just kind of cancel them out. So we're just left with P1 T1 equals P2 over T2. See that? So what's going to happen if the Earth is getting warmer? What's going to start happening to our atmospheric pressure?
Increase.
It's going to increase, right? Okay, questions, concerns, Cash?
No.
No. So, okay, so this basically just showing you the accumulation of carbon dioxide over the last billions of years. So not billions, thousands, hundreds of thousands of years. So you guys get an idea. Okay, so you can see where we're kind of at right now. You know, we're in a little trouble in 210 compared to where we were at before we started introducing ourselves into the situation. So our carbon dioxide is increasing steadily. So all of this is going to play a part in terms of the composition of the gases, how much pressure is going to be there. And then eventually, you know, we're going to start working on messing with that whole concept of volume. Although the gravitational pull does a pretty good job of keeping things under control, but there is going to be some type of pushback on it, right? And that's going to start affecting. Okay, questions, concerns, Cash? Good. Okay. So we're going to talk about diffusion and effusion. So diffusion is basically the process where molecules are distributed or dispersed in a space in response to differences in concentration or differences in gradient. Okay, so basically diffusion is it's a passive. It doesn't require energy. It's a passive way of gas movement. For instance, if we were in a classroom and Leslie tooted, okay, now would that gas surround Leslie? Or will that gas diffuse across the room?
Diffuse across the room eventually.
Eventually, right? But initially, it starts with Leslie. Leslie has the high concentration because she tooted, right? And the first one that smelt it, dealt it, that saying, right? You guys don't remember that from middle school?
Yes.
Okay, so now, in that case, you know, let's say Leslie is on one side of the room and Darlene is on the other side of the room. Eventually, Darlene is going to smell it, right? Why? Darlene, why are you going to smell it? Is it because Darlene is breathing heavy? I got to get a big whiff. Is that the reason why?
No.
Are you there, Darlene?
Yes,
Yes. So why are you going to smell it?
because it moves.
Because
Like,
gases move, right? We know the kinetics of gases. That's the premise of everything that we began talking about. Kinetics of molecules, right? Things move. So these gases are going to be moving, right? And they're going to be moving fairly fast, particularly since it's a high concentration around Leslie. So they're going to try to move to a lower concentration, right? To kind of balance it out. So you get that spread, right? So eventually everybody in the room would smell, well, depending, of course, how bad the fart is, right? I mean, the toot, my bad. Okay, are you there, Leslie? Since we're talking about your toot.
yeah.
Okay, so we're going from a high concentration, the one that's surrounding Leslie, to a lower concentration, right? Where Darlene is at on the other side of the room. And so eventually it spreads throughout the entire thing. Okay, so we can actually calculate the rate of diffusion. We can sit there and calculate how fast does it take Darlene to sit there and smell the gas, right? The rate of diffusion is just the amount of gas passing over a certain area over a given amount of time. Can't we do that? Mauricio, can we do that?
I think so.
Yeah, we
Not quite
can, right?
sure.
Because we could use Darlene's nose to sit there and determine, okay, we know how far that room is, right? So we can say that's our given area. So the amount of gas passing over that given area. So we get an idea, right, of the rate of diffusion. Okay, rate of diffusion is just going to be the amount of gas passing over a given area over a unit of time. Okay, so here's an example, right? We have two different gases. We have hydrogen and oxygen. So this stop cock is closed, right? As soon as we open the valve, the gases are able to intermingle. Now what's going to happen is, over time, because these gases are moving and they're obeying, quote, the ideal gas law, they're not bumping into each other and stuff like that, causing clogs. They're not sticking together, I should say, causing clogs or anything like that. So the gases are able to move, right? And because the gases are able to move, they're able to sit there and diffuse from a high concentration to a low concentration. And eventually they're going to move throughout the vessel so that they're evenly distributed on both sides. That is an example of diffusion, or actually, it's actually an example of effusion, because effusion is going through a smaller hole, essentially, right? So, but the fact that they're able to move from one side to the other side and they're getting to the equilibrium part, that movement going from a high concentration to a low concentration, that's diffusion. So effusion is when you're looking at a particular size of a container, right? So diffusion, we don't have that fine hole defining it. It's just the fact that it's able to move from a high concentration to a low concentration. Effusion is going through that fine little hole. Okay, are you guys with me?
Yes.
Yeah.
Okay.
Yeah.
Okay, so we have two different balloons here, right? We have in the orange, that balloon has helium. In the blue, that balloon has argon. Okay. After 12 hours, we notice that the helium is lower than the argon. Why do you think that is?
Because someone used the helium to make a funny voice.
Why do you say helium?
It has a smaller mass, I think.
Yes. So helium is smaller, right? And so the helium the helium gas, the helium atom, is able to sit there and effuse through the balloon, through the rubber of the balloon. So over time, its diffusion rate is faster than that of the argon. Argon is having a harder time getting through the pores of that balloon because it's a bigger atom, where helium as a smaller atom is able to get there and able to get through faster because you're having more of it going through than the argon does. You guys are with me?
Yep.
So it's dependent on mass of the atom.
Yeah, so it's going to be dependent on mass of the atom. That's true.
Right. Okay.
Right. And then also size. Size plays a part of it as well, too. So the size of it is going to play a part of it, and the mass is going to play a part of it. Argon is moving slower than the helium. The helium is lighter, right, in terms of mass. So it's able to sit there and get through faster because it's going to be moving faster. Room temperature is the same in both situations, right? So the lighter molecule is going to go faster. Are you with me?
Yes.
Okay,
Yeah.
so let's say I've
Yes.
had two different isotopes. Let's say two different isotopes of uranium. We have uranium 235, and we have uranium 238. Okay, what is the difference between uranium 235 and 238?
Neutrons.
The number of neutrons. Okay, that's true. What else is different?
Mass.
Mass. Mass is also going to be different. Okay, so which one would you expect to effuse faster? Uranium-235 or uranium-238? Which one is going to be? What was that?
235.
235.
235.
Yeah, because it's lighter, right? Okay,
Yes.
I'm a big guy, right? So I weigh about 220, okay? 220. So when I was 150, right? Do you think I move faster than I do at 220?
Yes.
No.
Yeah, I moved a whole lot faster, right? Because that mass is slowing me down, right? So that's the same thing that's going to happen with kinetics. Okay, are you guys with me? The movement of gases.
Yes.
Okay, good, good. Okay. Okay, so this is basically just showing you that. We know that the 235 is going to go faster. It's going to be able to diffuse faster because it's lighter, right? And so you're going to get a higher enrichment of your faster guy than your slower guy, right? Well, you can sit there and separate them based upon the kinetics of things. So this is one way that we are able to enrich isotopes, right? Because we know that one is going to be faster or slower than the other. So under the perfect circumstances, we're able to sit there and allow things to effuse and to diffuse, to sit there and allow for enrichment. Okay, so in this case, you have the uranium. This is so this is the mixture of uranium hexafluoride. We have the one that's higher and the one that's the one that weighs more, the one that weighs less, the bigger isotope. So the bigger isotope is going to be stuck in the middle. The smaller isotope is going to be able to effuse to go through here. And then so we're able to get the enriched version of the smaller isotope compared to our depleted version of the larger isotope. Okay, questions, concerns, Cash?
No.
Okay, good. Okay, so we've talked about the kinetic molecular theory, right? And that kind of makes sense so far? Kinetic molecular theory. What is kinetic molecular theory? Kinetic. What does kinetic mean?
The movement of molecules.
Movement of molecules, right? So it's a theory about the movement of molecules. So what is so far, what can we say about the movement of molecules? What is it going to be dependent on?
Temperature.
Temperature, right? So as temperature increases, molecules are going to move faster, right? So that's also, it's going to be dependent on temperatures. So what about with those isotopes? Was that dependent? Did one move faster than the other? And why?
Yes.
Why?
Mass.
Mass, okay. Okay, good. So we know that mass can be a dependent. It can affect that aspect as well too, okay? So we also know that all the other aspects, if we have pressure, that can affect it. If we have volume, that can affect it. So all of those things can affect those things, right? Because they all kind of are intertwined with each other. Oops. Okay. So here, this is basically just showing you everything that we've talked about and showing you how all four molecules are basically intertwined and how all four molecules can affect the kinetics of that molecule, okay? All four properties, not all four molecules, all four properties. To say amount or mass, you know. Okay, so yeah. Okay, so here we sit there, we're looking at the U represents the speed. So this U RSM is called the root mean average, or the root mean square speed. Okay. The UP is the most probable speed. Okay. So this here represents the speed because we have okay, so we have okay, so this basically represents the distribution of all of the different molecules, right? And so all of these different molecules can technically have different speeds because each molecule is slightly different from each other. Technically, they're the same, right? In theory, they're the same. Now, the thing that's going to affect the speed of the molecule is temperature. So if one, let's say, is higher up in the elevation and the temperature's lower at that case or higher at that case, then the speed of that molecule is going to be a little bit higher, right? If one is at a lower elevation, the speed of that is going to be a little bit slower, okay? So this here is just representing the speed of all of the gas molecules that are distributed over the entire time, right? And then this here represents the most probable speed. This here represents what we call, as I said, the root mean square speed, okay? Now, the major thing that you want to get from this is that it is going to be dependent on temperature. This tells you what the most probable speed is of the molecule. This tells you, it tells you kind of where you're getting breaking off. This is where take the average of everything, kind of where it's all going to lie at, okay? So if we take a look at this represents fractions at different temperatures of the same gas. So this is nitrogen. So as nitrogen increases temperature, you're going to have a wider distribution of speeds. A lot of the stuff is going to be moving faster, right? You're still going to have some of the stuff that's taking a little bit to get started, but you're going to have a distribution of each of those molecules of nitrogen. At a lower temperature, you're going to get a slower speed. At a lower temperature, even slower speeds. And at 100 degrees Kelvin, you're basically going to have pretty slow, right? So you're not going to have as wide of a distribution as your temperature increases, right? And those speeds are going to be dictated by the aspects of these molecules interacting with each other, right? Molecule-molecule interactions, intermolecular forces. So that's going to affect things as well. So those lower temperatures allow us to sit there and have those interactions. And because of those interactions, the molecule is going to slow down. Are you with me?
Yes.
Okay.
Yeah.
So knowing what you know, okay? Knowing what you know. So this curve kind of applies to other things as well. So if we looked at all of the noble gases, right? This representing the fraction, this representing the speed. So which ones would you expect to be moving fastest, having a wider distribution of speeds? Helium, neon, argon, krypton, or xenon? Knowing what you guys know. Okay, Jessica L. Preach, girl. What do you think?
Can you repeat the elements again, please?
I'll type them up for you. So we have these 5 elements, or 5 atoms, 5 elements. Argon, neon, and helium. Which one do you expect to be the slowest? Which one do you expect to be the fastest and the most distributed.
Would the fastest be helium?
Okay. So you're saying this curve right here. Okay, helium. Okay, so who's going to be the next? Mauricio. We'll pass it on to Mauricio. Mauricio is going to get the baton now. Mauricio?
Yes, I'm here.
Okay, which one do you think is going to be next? She says the fastest one, the one that's going to be the most distributed, is going to be helium. Which one do you think is going to be next?
I think the next one is neon.
Okay. Kayla.
Argon.
Okay. Alberto.
I'd say argon.
You're going to say argon? We already said argon. Do you think she has it in the
then.
wrong spot? Is that what you're saying?
Can I say helium?
Helium? Helium's already been said. So we got this one. We got this one. We got this one. Huh? You said krypton?
Yeah.
Okay. And so that means the slowest one is going to be who?
Krypton.
Is it going to be krypton or xenon? Okay. Why? Why is that the case? Why is it set up like this? What are the distinctions between all of these argon gases? I mean, not argon gases, all of these noble gases.
The weights.
The weight. Who's biggest? Who's fattest? Who's got the biggest butt?
Excellent.
Xenon.
Xenon. Xenon got the biggest butt. So it's going to be moving slower than krypton. Okay. Then argon, right? So the slowest one of all the noble gases, if we even put radon up here, is going to be radon because he is so big compared to all of the others. There we go. Radon would be something like this. Okay. Are you with me? Oops. Questions, concerns, Cash?
No questions
No
on my
questions.
behalf.
Okay. Okay. So last thing is non-ideal gas behavior. Oh, so this is just basically just showing you that, right? So because the speed is going to be dependent on the size of the molecule, right? That's going to play a part in it. So molecular mass is going to play a huge part in your molecular velocity. So as you increase in molecular mass, your molecular velocity is also going to increase. Okay. Okay, so non-ideal gas law. So this basically is the formula for that. This is the ideal gas law. This is the non-ideal gas law. So the non-ideal gas law actually corrects for those attractions, those intermolecular forces, van der Waals effects. So it actually calculates those aspects. So these are just the corrections for that. So here we have P plus AN, where A represents a constant, N represents the number of moles, B still represents volume, times V minus number of moles times another constant, right? So that A constant and that B constant are given to us in tables, and we can just plug and chug to sit there and do the calculations, okay? Questions, concerns, Cash? So under non-ideal conditions, gases are going to behave non-ideally. So we would use this equation under those circumstances. And again, your A is going to be given to you, and your B would be given to you in those circumstances. Are you with me?
Yes.
Okay. Okay. So this basically is a graph, and this just shows you Z is basically, it's called the compression factor. It's a nice way of just showing you the distinction between ideal circumstances and non-ideal. Okay, so you can kind of see these are the pressure. So as we start to get under high pressure, we start deviating from ideal circumstances. Ideal circumstances basically says that your Z, your compression factor, is going to be 1, right? And so it's going to be a single line completely straight across, where under high pressure, you deviate completely from that. And it doesn't matter the gas that you're talking about. Okay? So yeah, are you with me?
Mm-hmm.
Yeah.
Okay. Okay, so, and this basically just shows you what is ideal. Ideal, these guys are just acting independently and they're not interacting with each other. It's all perfect and happy-go-lucky. This is what really happens. You're having interactions between molecules. And because those interactions between molecules, then they're going to get stuck. They're going to stick together. They're, and the collision force, you're not going to get that nice bouncing off of things. You're just going to get things like clogging, in that sense. And so real case, ideal case. So in the case of the container itself, so under the ideal situation, you just get things bouncing completely off of each other. But really what happens is these guys, they interact with each other and then they kind of get stuck to the wall, or so they're not going to be able to bounce off the wall the way that we expect. Okay. And so those are, when we look at the actual results, these are some of the factors that are being taken into consideration, right? So that's the reason why, if you're doing things experimentally, right, ideal is giving you ideal circumstances, but we know that it doesn't always add up to actual circumstances. Are you with me?
Yes.
Okay.
Yes.
Good. Okay. Okay, that's it. That's the whole chapter. I should give you one other thing. So, we have to meet and talk about your lab. I'll give you guys an opportunity to pull up your data because you guys have it already in Excel, right? Or a spreadsheet, right? So that we can play with.
Yes.
Is that true?
Yes.
Which lab?
The balloon lab.
18.
Oh, okay. Thank you.
There's one other thing that I want to give you before I go. Remember, off my head.
Is that WRMS?
That's U. Sorry,
U.
U-R-U-M-S. U-R-U-M-S. And this, I should say, this is a special M. It's molar mass in kilograms per mole. Okay. Just in case you came across it. Okay. Okay, so I'll see you guys in lab in 5 minutes, 10 minutes. See you guys in 10 minutes.
What lab are we doing? Oh, we're the 18?
Yep.
Okay.
Dr. Henry,
Sometimes, Christian, I think you don't pay attention to me.
that equation that you just put up was for the non-ideal gas?
No, it's just, that one is just for molecular theory. The
Okay.
one for non-ideal gas is the one that I gave you earlier. Although you, let's see. Let's see. So that's the one for non-ideal gas.
Okay.
So this one for when we're talking about kinetics, molecular velocity.
The square root 3RT over the special molar mass.
Yep.
Okay.
Okay. Questions, concerns, Cash, credit?